All right, so welcome to chapter 3, where we're going to talk about least squares regression line and explanatory and response variables. We're starting out with scatterplots. So a response variable is measuring how a study comes out, okay? And so the variable is like if you're doing an experiment or some study, longitudinal study, you want to see like how much growth did they have or what changed, right? And so you're measuring something at the outcome of a study, okay? The explanatory variable helps explain or it influences changes in the response variable, all right? So sometimes it influences the response variable, and that's when you start getting into the idea of cause and effect, but it's not always cause and effect. Sometimes it can help explain it, all right? And there's cases where they're actually interchangeable. It's not obvious which one caused which, and so it's like, which one do you want to put where? And so a quick example is hand size and height, all right? People with bigger hands tend to be taller. Does their big hand cause them to get taller? Or does them being tall cause them to have big hands? No, it's just that one helps explain the other, okay, and helps predict the other, all right? It's not always a cause and effect relationship, and so we don't want to assume cause and effect, and that's one of those big things that we need to be cautious about, is not assuming cause and effect, okay? When you make a scatter plot, you're going to put your explanatory variable on the x-axis and your response variable on the y-axis, and they're both going to be quantitative variables. We're not comparing categorical variables here. We're comparing quantitative variables, all right? And whatever your explanatory variable is, you sort of want your whole range of the explanatory variable to sort of divvy up your x-axis and your whole range of your response variable to divvy up your y-axis. You don't need to start at 0, right? If this is year, okay, I'm not going to start at the year 0 if I'm focusing on the year 2000 till the year 2020, because then it would all be blank here, and then all my data would be over on the right. Take the range of your data and split it on the x-axis, change the range of your y data and put it on the y-axis, okay? And you want to label, you want to put some tick marks on here. So still label, tick, tick, tick. No, tick, tick, label. Yeah, give it a title, all that good stuff. All right, and then you get something like this. Okay, so this is the scatter plot of the mean SAT math score. Okay, so there's the mean SAT math score in each state. So there's 50 dots here. Each dot represents one state against the percent of the state's high school seniors who took the SAT. And this was in 2005. Colorado is shown, and the two variables are 26 is the explanatory, so the percent taking the SAT. 26% of students took the SAT, and the mean SAT math score was 560. All right. And there's interesting reasons that might explain why the curve is like this. But if you're going to force all your population to take it, then you're going to get a lot more kids who are scoring lower as you make more of them take it. And if you're allowing only the kids who want to go to college to take it, a smaller percentage of kids taking SAT, they're going to be the most motivated ones taking it, and they're the ones who are going to score highest. Okay. So, people that are scoring high is really good, and people that are right and high up, like Colorado, are some of the best, okay? But a scatter plot, notice the percent range from 0 to 100. The SAT score, they didn't go and start at 0. They started just below their range. So they went from 460 to 620, so it fills your page, all right? And we'll talk about how to interpret these and stuff in a minute. Big idea, explanatory, percent taking SAT, and response. There may be a little cause and effect here, but we don't want to presume cause and effect, okay? See ya.